Section 5.4 talks about the Pythagorean theorem and also its converse. So we're focusing in on just a few things from this section. We are skipping some things, but I will go through just the relevant points that I'd like you to know. So first of all, we can use the Pythagorean theorem to classify triangles, and we use both the theorem and its converse. So the theorem would say, if we have a right triangle, then, and with side lengths of A, B, and C, with C being the hypotenuse, okay, if all of that's true, then we know that A squared plus B squared is C squared. The converse would read the other direction, and we would say that if this relationship is true for the three sides, that A squared plus B squared is C squared, then that means the triangle is a right triangle. We can also classify acute and obtuse triangles based on the side length relationships. Okay, so it's kind of interesting if you look at A, B, and C, with C still being the longest side, even if it's not the hypotenuse. Okay, maybe there is no right angle, so it's not called a hypotenuse. But it turns out that if the longest side C squared is greater than A squared plus B squared, then we have an obtuse triangle. Okay. And then a quick review of triangle facts. The longest side is across from the largest angle, and the smallest side across from the smallest angle, and the middle side and angle across from each other. Okay, so if C is the longest side, then we know that that obtuse angle is the one that's opposite from C. And then similarly, if C squared is less than A squared plus B squared, then it's an acute triangle. And then if C is the longest side, then the angle across from C is still the largest, but in an acute triangle, all three angles would be acute. So those are the three cases. Okay, so equals is right, greater than is obtuse, less than is acute. All right, 3 facts from section 3.5. This is a section that we skipped, but these are just handy facts to know. So here are the first 2 that I briefly just mentioned. So the larger angle goes with the longer side, and the shorter side goes with the smaller angle. All right, and then this last one is important. We have some restrictions on lengths of sides that can actually make a triangle. So in order for 3 numbers to represent the lengths of a triangle, so for instance like 6, 5, and 3, okay? So if we want to know, could a triangle have lengths of 6, 5, and 3, we need to make sure that the sum of the lengths of any 2 sides of a triangle are greater than the length of the third side. Okay, so in other words, 6 plus 5 must be greater than 3, 5 plus 3 must be greater than 6, and 3 plus 6 must be greater than 5. And it turns out you don't actually have to check all 3 of those every time, but it's sufficient to just check the sum of the 2 smaller ones. Okay, so like for instance, 6 plus 5 is guaranteed to be bigger than 3 just because each of these is larger than 3. Okay, and I know that 3 plus 6 is greater than 5 every time because I've got 1. If the 6 is bigger than 5, then adding in the 3 certainly doesn't change that. So we really only have to worry about the case where the 2 things that you're adding are both smaller than the third number, and then we want to check and make sure that their sum is larger than the third number. Okay? So this set of lengths here would be possible. You could have a triangle with lengths 3, 5, and 6. Okay, so we're going to put those facts together with the Pythagorean theorem and sort of those related inequalities to classify these triangles based on the lengths of the sides. So there's a trick. Even though that's not explicitly mentioned, we do need to make sure that these actually do represent possible triangles. So real quick, I'm just going to go through and add the 2 smaller sides and make sure it's larger than the third one. Okay, so 4 plus 5 is 9, which is greater than 7, so that is a triangle. Okay, or it could be. 6 and 7 is greater than 8, that's a triangle. 9 and 12 is greater than 15. 3 plus 4 is 7, which is not larger than 9, so D is not even a triangle. Okay, then the 3 remaining ones, I'm going to use the Pythagorean theorem to decide what type of triangle it is. So we're going to take the longest length in each case and let that be C. Okay, so in the first one I would have 7 squared, and I want to see if that's greater than, less than, or equal to 4 squared plus 5 squared. Okay, so we end up with 49, and then on the right we have 41. Okay, so C squared is greater than A squared plus B squared, so this would be an obtuse triangle. And then the greatest angle would be across from the side measuring 7. Okay, 6, 7, and 8, so I would choose the largest one as C. That's 8 squared, and then I want to see if that's how that's related to 6 squared plus 7 squared. So we have 64 on the left and 85 on the right. So C squared is less than, so that would be an acute triangle. And then we tried the third one, so we would check 15 squared and compare that with 9 squared plus 12 squared. So on the left we have 225, and on the right we have 225 as well. Okay. So those are equal, and that means that that is a right triangle. All right. The textbook also has a chart that gives you some of the common Pythagorean triples, or in other words, sets of numbers like this that are that form a right triangle. Okay, so some of these you can recognize easily by memorizing some of the more common ones. So one of the more common triples is 3, 4, 5, right? And any multiples of that would also be a right triangle. So you can see 9, 12, 15 is just the multiple. If you triple all of those, you get 9, 12, 15. So if you can recognize that, that's another way to check that it's a right triangle without having to go through the actual math to see that A squared plus B squared equals C squared. Okay, let's use the Pythagorean theorem, and this is an interesting one. We can use it to find the height of a triangle just knowing the lengths of its 3 sides. So this is going to be really useful when we get to the area of a triangle, or actually even in real life. Like let's say you know, let's see, let's pick out one of these ones, 6, 7, 8. Okay, maybe a different one. Right, and if you want to know the height of the triangle, we can actually figure that out, and then we can find the area. Okay, so your textbook has given you a diagram to help out. We don't actually need the diagram. We could have created it ourselves from the given information. Okay, so here it is. 4, 5, and 6 are the side lengths, and then we want to find the length of the altitude to the side of length 6. So you would drop a line segment from this top vertex between 4 and 5 down to 6, and then by definition of an altitude, it's got to meet it at a right angle. All right, so notice first of all, this original triangle is not a right triangle, but when we drop this altitude, we do get 2 smaller right triangles. So our strategy is going to be to use the Pythagorean theorem on those 2 smaller ones, and then hopefully be able to solve for this height. So we have 2 variables necessary. We have the height that we don't know, and then we also don't know how this side of 6 is split up. Okay, so we're going to call one portion of it x, and then the other portion will be 6 minus x. Alright, so I can use the Pythagorean theorem on this left triangle, and I would write x squared plus h squared is 4 squared, or 16. Okay, so remember it's always the side across from the right angle that is C. And then I do the same thing for the triangle on the right, so we would get h squared plus 6 minus x squared equals 5 squared, or 25. All right. I'm going to simplify this one a little bit by working out this parentheses. So remember that exponents don't distribute, so we actually need to do FOIL with that. So I need to do 6 minus x times 6 minus x, and we're going to get 36, and then the two middle terms, minus 6x is minus 12x, and then plus x squared is the last term. Alright, so that equation becomes, let's see, h squared plus 36 minus 12x plus x squared equals 25. Okay, so what we have now is a system of two equations, and we have two variables, h and x, so we should be able to solve this. It's not a linear system, they're not lines, they are quadratic equations, but we can still solve these for x and for h. So we can use actually the same two methods we do for linear ones. We can do either substitution or elimination. So I'm going to show you a couple different options. The first one I like is to look through and find if there's a similar piece to these that we could substitute. So like here's an h squared and here's an h squared. So what I would probably do is just rearrange this first equation to get h squared by itself. So this one would become h squared equals 16 minus x squared. And then I can substitute that into the second equation in place of h squared. Minus 12x plus x. And that's a squared. I messed that one up. Okay. And now you can simplify, combine like terms. So this is kind of nice. The x squareds cancel. And if you subtract 36 and 16 to move them to the right, you end up with negative 12x equals negative 27. And when you divide, you get x equals, and then I'm going to leave this as a fraction and just simplify, but this is going to be 9/4. Okay, so double check that on your own if you need to, but negative 27 over negative 12 simplifies to 9/4. Alright, so why do I choose to leave that as a fraction? Couple different reasons. One, if the decimal was repeating, then I would want to leave it as an exact answer here rather than rounding, since I'm sort of in the middle of the problem. Another reason is because the next thing I need to do is solve for h squared, and I'm kind of looking ahead up to this equation. I'm going to substitute 9/4 in for x, and I see that I need to square it. So I prefer fractions for squaring because I can do those mentally without needing a calculator. If you have a calculator, maybe it doesn't make a difference to you whether or not you use a fraction or decimal. Okay, so then next step, substitute x in for x squared. I'm going to erase some of this so I have some room to work. Okay, so into this equation we would have h squared equals 16 minus 9/4 squared. So that becomes 16 minus 81 over 16. So I'm squaring the 9, squaring the 4. And then we need a common denominator to subtract. Okay, so let's see. X is 9/4. Alright, so I'm going to make these both 16ths. So 16 becomes 256 over 16. Subtract 81 over 16. And you get 175 over 16. Okay, And then the only factors that go into 16 are just powers of 2, 2, 4, 8, 16, etc. And they don't go into 175, so that fraction is fully reduced. Okay, so that's an answer for h squared, and then we need to find h. So my last step, I need to square root this to get h. Okay, so h would be the square root of 175 over 16. And technically it should be plus or minus, especially in an algebra problem, but I know that h represents a height, so that's going to be just the positive answer. Okay, so I'm going to go with the positive square root. Okay, this becomes square root 175 over 16. I'm sorry, square root 16, and then I can square root the 16 to get 4. All right, and then we need to simplify the numerator. Okay, so that becomes square root 175 is square root of 25 times 7. And 25 can be square rooted, so this becomes 5 square root 7 over 4, and that's as simple as it gets. Okay, so h, the height or the length of the altitude, would be 5 square root 7 over 4. All right, and then you may just want to, to double check that, so get like a decimal answer for this original fraction we had for h, and get a decimal answer for this, and verify that they are the same thing. Okay, so that's one way to solve this. There's another one given in the textbook, and it's kind of like the elimination method. Basically, you add or subtract the two equations together in such a way that one of the variables will cancel. So usually you line these things up. Okay, so I would probably do, let me go back to the original that we had here. Yeah, let's do that. Okay, so this was 6 minus x squared. Okay, so what I would do is notice that the h squareds are both on the left. Okay, so if I subtract these two equations, I'm subtracting like this whole side minus this whole side. Okay. So we would end up with x squared plus h squared minus, actually maybe this is easier to do it this way. So basically you want to subtract like terms when possible. Okay, so I would do h squared minus h squared cancels, and then the other terms that I have would be x squared minus 6 minus x squared equals, and then I would do same order, so first equation minus second on the right, so we do 16 minus 25 is negative 9. Okay, and then I would still need to FOIL this 6 minus x squared. So this is going to be minus, and then in parentheses, 36 minus 12x plus x squared equals negative 9. And then you would go through and distribute the negative, so you would end up with negative 36 and positive 12x and negative x squared. Okay, so then the x squareds would cancel, and then when you combine like terms and everything, you've got 12x equals 27, and we're back to the same place where we were before. When you solve that, you're going to get x equals 9/4. Okay, so basically it's still the same two options, either substitution or elimination by either adding or subtracting the two equations. All right, so those are the highlights for section 5.4. So using the Pythagorean theorem to decide whether or not a triangle is right, acute, or obtuse. There are some simpler examples with using the Pythagorean theorem, So for instance, if you know that there's a right triangle and you know that one side is 7 and one is 25, and you need the third side, okay, using Pythagorean theorem to solve for that. And then I did one of the more complicated examples, which was using it to find, using it to find the altitude of a triangle.